Okay, let's wait maybe 2 minutes before we start, just to make sure that okay, it's 1 p.m. So nice to see you again, everyone. I'm Claudio Menghi. It's a pleasure for me to introduce you to the third session of FMTIA. I hope you had a great, quick lunch. So let me first introduce the keynote speaker for this session. It's my pleasure to have Jeremy Avigad with us. So he's a professor at Carnegie Mellon University. He's a director of the Hoskinson Center. He's an expert on the Lean theorem proving. And he's going to give us a keynote on teaching logic and mechanized reasoning with Lean 4. So welcome, Jeremy, the floor is yours.
Thank you, Claudio. So let's see, so let me share the screen. And okay, so I think everybody is looking at the screen with my slides. So if that's not the case, please do speak up and let me know. But so I'm going to be talking about a course that I'm teaching, co-teaching with Marijn Hulle and Wojtek Nawrowski. And we're excited about it. So I'm excited to tell you about it. So the course is a new course in the Department of Computer Science at Carnegie Mellon University. The course number is 15217. It's called Logic and Mechanized Reasoning. And Wojtek is our teaching assistant, so he's a second-year PhD student at Carnegie Mellon. So 15 indicates that it's in computer science, and the 200 level means that it's appropriate for second-year students, undergraduate students in computer science. So students in the course are required to have taken 15150, which is a introduction to functional programming, and also the course 15151, which is called Mathematical Foundations for Computer Science. And also first-year undergraduate students at Carnegie Mellon in computer science are required to take an imperative programming class as well. So in the second year, for coming into the course, we can assume that they've got some programming behind them and also some basic mathematics. In this first iteration, the course is small. We have only 11 students. Students at Carnegie Mellon seem to be reluctant to take a new course, but the ones that are there seem to be enjoying it very much. So we're hoping that it will grow over the years. So let me read you the course description. So we say symbolic logic is fundamental to computer science, providing a foundation to the theory of programming languages, the theory of databases, AI, knowledge representation, automated reasoning, and formal verification. Formal methods based on logic complement statistical methods and machine learning by providing rules of inference and means of representation with precise semantics. These methods are central to hardware and software verification and have also been used to solve open problems in mathematics. So this first paragraph is really meant to advertise the course to students and to convince them to take it. And since all of them want to do machine learning, we have to either tell them or remind them that symbolic methods also have important applications. But here's the more focused description of the course. So the course is an introduction to symbolic logic on 3 levels: theory, implementation, and application. We will present the underlying mathematical theory, and students will develop the mathematical skills that are needed to design and reason about logical systems in a rigorous way. We will also show students how to represent logical objects in a functional programming language, Lean, and how to implement fundamental logical algorithms. Finally, we will show students how to use contemporary automated reasoning tools, including SAT solvers, SMT solvers, and first-order theorem provers to solve challenging problems. And we will show students how to use Lean as an interactive theorem prover. So there's a lot there. But I'm going to try to convince you that we really do manage to pull it off. So I think the most notable feature of the course is what I just described, that there are really 3 things going on at once, right? So on the one hand, we really want to convey logical theory to students. So just the basic mathematical introduction to the syntax and semantics of classical propositional logic and classical first-order logic. But then we also want them to be able to code things up. So, so for implementation, we have them just coding up formulas and manipulating them and evaluating them and things like that. Finally, we want them to be aware of logic-based tools out there, so specifically SAT solvers, SMT solvers, and first-order theorem provers. And we want them to understand what they do and how to use them and be able to use them on their own. So that's, I think, the kind of the main thing of the course, that we really try to give these roughly equal weight, maybe a little bit more on the theory, maybe a little bit less on the application, but almost, roughly thirds, kind of in parallel. But another notable feature of the course is that it's based on Lean 4. So I'm going to say something about that choice. So in addition, they also use tools like Catechol, Z3, or an SMT solvers like CVC4, CVC5, and Vampire. And we arrange it so that it's convenient. They can actually call them from inside Lean. So Lean is always the front end. So here are some of the mechanics of the course. So we're writing the textbook as we go, which has been a little bit crazy, but it's coming out well. And I'll show you that in a second. So it's in HTML, and also there's a PDF version. There's an associated GitHub repository for the course they can run in Gitpod. And then there's a course webpage. So let me see if I can kind of show you that briefly. So here's the course webpage. Maybe I can make it a little bit bigger. And here, you can find it online, and here's the schedule of classes and all the assignments. So there's so you can go take a look at that. But here's the textbook. So it's created with Sphinx, the read the docs mode, and I'll come back and I will say more about the textbook. We'll look at the table of contents. But so there is an online textbook that we've been writing, and it compiles to a what's going on. Seem to have frozen. Oh, there we go. Sorry. So it compiles to a PDF version as well, and it's got more than 100 pages, which is not bad for a semester's worth of work. And it seems to be frozen there. Sorry. Let me close the course page. Yeah. So that's mostly what I need to show. And then there's So here's the course repository with the README file. And so students have two options. They can either pull the repository and run Lean in VS Code on their computers, which is what most of them do. But let me show we also have it set up in Gitpod, so that if you have or if you set up a Gitpod account, you can just kind of run it in your browser, and anybody can. So you can go to the webpage now and do that. And maybe I'll leave it running for yeah. Let me leave it running for a few seconds, but it takes a little while to start up. But yeah, so let me leave it running and we'll see what happens when it comes back. Oh yeah, oh no, that's good. Let's see. Yeah, so there it is. There's Lean, there's the course. Yeah, and there's examples. So yeah, so as simple as that, they have they've got Lean running in the cloud and everything they need, and they have a VS Code front end. Right, so that makes it convenient for them to use. But as I said, most of them will be running it just in VS Code. And so for the examples, when I show you things to class, they'll be running in VS Code as well. And so the repository consists, I mean, it's basically, a library of stuff we've given them. But the main thing is that all the examples in the textbook, they have there. And they can kind of run and evaluate in real time. Okay, so I'll come back to that and show you more examples. Okay, so that's the mechanics. That's how things go. Let's see. There we go. So let me let me go back. And so let me just go over the table of contents and tell you what's in the textbook. So there we go, back. So yeah, so the course is, there's a chapter on just ordinary mathematical background. So it's just induction and recursion and generalized induction and recursion. So in this chapter, we use things like lists and well-founded trees, but of course we're heading towards, induction and recursion on syntax. We give them an introduction to how to basically using Lean and using Lean as a programming language, and I'll say more about that. But then just an ordinary, mathematical introduction to the syntax and semantics of propositional logic. But then we, show them how to code it up and put things into, negation normal form and conjunctive normal form and so on. We talk about decision procedures for propositional logic. I mean, we show them a little implementation of DPLL and Lean. We show them, we talk about the Satan transformation. We show them an implementation of that. But then, you know, a really cool aspect is that we show them how to use SAT solvers and call them from Lean, and we give them combinatorial, so examples of combinatorial problems that are solved from within Lean, and then they have exercises, they have homework to do similar ones. We talk about proof for propositional logic and proof systems, and you know, we talk about, for example, how you can extract a resolution proof from when DPLL comes back and determines that your formula is unsatisfiable. There's a resolution proof in the background. We show them how to do propositional logic and Lean. And then and here is just using Lean as a theorem proofy here. Right. But then we do first order logic, go through the same thing, syntax, semantics, and so on, and implementing terms and evaluating them, and formulas over models with a finite domain. A little bit of decision procedures. We talk about linear arithmetic, linear integer arithmetic inequality. Show them what SMT solvers are, and again, show them examples. And I'll, you know, as time allows, I'll show you some of those. And this is pretty much where we are now. So there are just a few lectures left for the course, and what remains, we'll be telling about deduction systems for first order logic and how to use first order theorem provers like Vampire, and then kind of everything else to, you know, squeezed in. There we go. Okay. So that's a quick overview of the course. So let me say something about the choice of Lean. So we agonized over the choice of Lean as a platform. So, you know, the main concern is that it's you know, not a finished project. It's still in pre-release. And for that reason, there's very little documentation out there. It's very, very limited. And also, Lean 3 is a proof assistant, has a large mathematical library. There's very little of the mathematical library for Lean 4. But on the other hand, you know, mitigating factors, Lean held up pretty well, so we didn't have any serious problems, you know, with the implementation. As far as the limitation of documentation, you know, the saving grace is that most of the assignments, you know, most of the things that we had students do were supported by the examples we showed them in class. You know, we showed them enough code and how to do enough things. They had enough examples in front of them so that whenever, you know, they were looking to do something on their own, they could start pretty much by cutting and pasting things that already existed. So that you know, that worked out okay. And we really didn't need a big library of formal theorems. The course isn't about formal theorem proving. So really, we were just using Lean 4, you know, mostly as a programming language. So what were the benefits? Well, so there were a lot. So first of all, as we'll see, you know, as a functional programming language, you know, it's really great for implementing logic. And just as, you know, as evidence for that, Lean itself is implemented in Lean. So it really is good for implementing logical systems. But I'll show you that the language has some imperative features as well. And those were really essential for a lot of things we did. The most natural way to, you know, code something up was just to write a loop and use arrays and so on. And you can do that in Lean. I'll also show you that there's some special purpose syntax that was really useful for preparing examples that students could explore. The editor interface was great. It's not like a notebook. It was like a proof system with continuous compilation in the background. So you can sort of type things in and constantly, you know, get feedback. And students really liked it. They really liked the language and the syntax. So just to give you some examples. So, you know, for example, in the mathematical presentation, when we tell students, you know, what propositional formulas are, we just do the usual thing. We say that, you know, it's generated inductively as, you know, variables are formulas, and true and false. And if A is a formula, so it's not A, and if A and B is so are A and B, A or B, A implies B, and A if and only if B. Right. And then a week later, when we're showing them how to implement it in Lean, you know, they get this definition. And, you know, once you get used to, you know, functional programming, you know, the way you read this is that, you know, the propositional formula is an inductively defined type. But, you know, for every string X or P, you know, var P is a propositional formula, and so are true and false. And if A is a propositional formula, you know, not A is, and so, you know, conjunction, disjunction, implication, and by implication. So it really does, you know, follow the informal presentation exactly, right? And that just keeps going. right? So in the informal presentation, we say that if you have a, an assignment of terms to variables, you get a notion of substitution, where to substitute for a variable, you just apply it. And, to substitute for a compound term, well, you just substitute for the subterms, and then you just stick the head F in front. And then when you code it up, there it is, to write the substitution function, given a first assignment of terms to variables, is a function of terms to terms. And to substitute for a variable, you just apply it. And to substitute for, F applied to a list of terms L, well, recursively, you apply the substitution to, all the terms in L, and then you just stick F at the beginning. So here partial stems from the fact that as a theorem prover, lean 4 can't yet verify termination. So here we're stepping outside the formal system, but so partial will just let you do arbitrary recursions. But that's okay. We don't mind that. We're not going to be really proving things about that. And lean 4 will get there. So the idea is that ultimately it'll compile these down to primitive recursion. Okay, but it keeps going. So I mean, I was trained as a mathematical logician, and so when you talk about model theoretic semantics, when you say what it means for a formula A to be true in a model M relative to a truth assignment, assignment of values sigma, well, you say that to evaluate the formula T equals T prime. Well, you evaluate the term in the model, each of the terms T and T prime, and then you just test whether they're equal. And to evaluate, an atomic formula of this form, well, again, you evaluate the terms in the model, and then you interpret the relation in the model, and then you apply that interpretation. And true is true, and true is false, and and or, just and or, and so on. And then existential quantifier, to evaluate exists XA. Well, you check whether there's some value in the universe of the model such that when you substitute that for A, when you add that to the assignment, the resulting formula becomes true in the model. Right? And we talk about this and we emphasize the fact that really everything can be done computationally except for the last two. When you have quantifiers, when the universe is infinite, you wouldn't expect to be able to do this. But when the universe is finite, you can. And we show them that, and we write down this definition. So here, the notion of a model, it really is a finite model, right? The universe is required to be given by a list of elements that you can iterate over. But same thing, you have a model, you have an assignment of values from the universe of the model to the variables. And every first order formula, evaluates to a Boolean. And the definition is really exactly the same. To evaluate the formula T1 equals T2, you evaluate T1 and T2 in the model, right, with respect to the interpretations of the function symbols and the assignment, and then you just test whether they're equal. Or to evaluate the relation, right, you just recursively evaluate the all the terms that the relation is being applied to in the model. You interpret the relation R in the model, and then you just apply the interpretation and so on. And the exists and all, they just apply to functional programming terms, any and for all. You just evaluate the list and then apply. So these are all draws, right? So with a functional programming language, it's really nice for representing basic logical operations. But lean also has imperative features. I mean, you can do this to test primality. You can just write a loop. So if n is less than 2, it's not prime. Otherwise, you just loop from 2 to n, and you just test. I mean, it's just a naive test. So if anything divides n, you return false. But otherwise, once you get to past the square root, then you're good. You return true. And the idea is lean internally represents, I mean, this is syntax on top of this becomes a functional representation, but then the compiler is smart enough to compile it to the right thing. So this really does, compile down to a loop. Also, lean has dynamic arrays. And so you can initialize array and add values, or you can kind of extend it, dynamically and push things. So this just does a multiplication table, just, rows and columns and so on. It just, puts yeah, but you can do it. So it looks like, again, there's clever functional trickery. It looks like you've got a mutable variable and you keep adding to it. But this really does compile down to something functional, but for which the compiler then translates it to efficient code. And so, I mean, this is really good. Later I'll show you that we code up Sudoku puzzles to send them to sat solvers. So conjunctive normal form formula. It's a list of clauses, and the clause is a list of literals. And to code up things, you really just want to do loops. So this is, for example, so let's see. So if you have like a 5 dimension 5 Sudoku, then it's basically 25 by 25 is the size, right? There are 5 by 5 squares. But for anyhow, so each cell contains a number. You just kind of loop from 1 to 25, and I mean, you just have to make literals and make. So here you're using a functional idiom to put together the relevant clause. You build the CNF formula. And so again, you can do this with a functional program, but this is really just very natural just to do just with a loop and building arrays and so on. So that's what we do. Another nice feature of Lean 4 is that in terms of syntax, the syntax is very flexible. So back when I showed you, where was it? The definition of propositional formulas. So if you want to, just build some by hand, what you have to do is you have to, if you open the namespace, you can write, to write P and Q implies whatever. You can do conj and var P, var Q, and impl. But we don't want students to have to write that just to write examples. And so, Lean gives you very flexible mechanisms to define your own syntax. And you can really do just about anything. Because Lean is implemented in Lean, the internals are exposed. You can really implement any syntax you want if you have the time and the energy to figure out how to do it. But they're fairly straightforward ways just to do simple things. And so, it's easy just to give them syntax for writing propositional formulas. So the idea is you type this into Lean. And this is just syntactic sugar for an expression like this. And so we have propositional formulas and assignments to propositional variables. So this is a partial assignment that maps P to true, Q to false, and R to true. And then you can evaluate the formula relative to this assignment. Here you can write down conjunctive normal form formulas. So again, this is a list of clauses, but it's just a convenient way to write it. And so you can say, here's a propositional formula and now convert it to conjunctive normal form. And so here's just another example of the kinds of things we can do. So, we kind of get students to try to understand what something like this means, right? So this says if you take a term T and you substitute S for X, and then you evaluate it semantically relative to the assignment sigma, well, you get the same result as if you evaluated sigma under the assignment sigma, interpret X as the result, and then evaluate T under the modified assignment, which is really kind of inscrutable, but then you can just do it, right? So we give them an interpretation of symbols like plus and times. It's easy again to represent that. But so here's the term, x times 2 plus y plus 3. So we just give them 3 terms. And here you can see you can do 2 things. You can either substitute the second and the third. So the first one has variables x and y. And the third one has the second and the third have the variable z. So you can either substitute the first formulas 2 and 3 for x and y, and then evaluate it under the assignment that maps z to 7. Or you can evaluate the subterms under the assignment that maps z to 7, right? And then evaluate the main formula under the assignment that maps x and y to those. And in class, you can get students to do this in their head and do the result. And then you kind of hover over the evaluation and see that they come out the same. Right. And finally, we use Lean as a proof assistant. So this is propositional logic in Lean and a simple proof by induction. So we haven't done this yet. There are a few lectures left in the class, and we'll hopefully I'll get a chance to show them that in the last couple of lectures. Okay, so again, just summarizing. So the reasons that Lean 4 is a good is good for that is that as a functional programming language, it's great for implementing logic. It's got the imperative features. It's good. The special purpose syntax is useful for examples. The editor is great for interactive exploration. We also, as an added bonus, we get it as a proof assistance, and it's got nice language and syntax. Okay. And okay, so what I'd like to do now, and spend most of the remaining time, is to give you a sense of the tasks, the types of things that we ask students to do, because that'll give you a sense of the kind of skills that we try to convey. So again, remember, we're doing 3 things in parallel. We're trying to give you theory, give them theory, basic logic. We're trying to show them how to code it up. We're trying to show them how to use the tools. So let me just go through each of these in turn. So as far as theory, we just start with things that have nothing to do with logic at all, but just basic mathematics, just to get them in the mood. So thinking recursively and proving things by induction. So we talk about the recursive solution of the Tower of Hanoi problem and show that you can solve that with n disks. You can do it in 2 to the n minus 1 steps. And so for the homework, we asked them to try to give a coherent argument that this is optimal, that you can't, solve Tower of Hanoi with less than 2 to the n minus 1 steps. Or, for example, we give them the recursive definition of the GCD function, right? And we point out that, the reason the recursion is well-founded, that, it's decreasing in the second argument. And then based on this description, we ask them to prove basically Bezout's theorem that for any x and y, you can find integers a and b such that you can write the greatest common divisor as ax plus b times y, right? And so, it's an induction that follows the recursion, but we make them struggle with it and figure out how to do it. But then we get to syntax, and there's a lot of induction and recursion on syntax. So, for example, we give them the recursive definition of what it means for A to be a subformula of B, which really means that we're giving them a recursive description of the set of subformulas of B, right? And we ask them to show that for any, A, B, and C, that if A is a subformula of B and B is a subformula of C, then A is a subformula of C. Which is tricky, which takes some thought. And similarly, we asked them the fact about substitution, for propositional formulas, that if you substitute B for P and evaluate it under tau, that's the same as doing the evaluation and substitution. So again, they're really exercising their skills at induction and recursion. Sometimes the most challenging problems really just involve unpacking definitions and semantic definitions in particular. So, we tell them what it means for a formula to be true under an assignment, what it means to be valid, what it means to be satisfiable. For entailment, we say that roughly, a set of propositional formulas gamma entails A, if every truth assignment that satisfies everything in gamma also satisfies A. And then we ask them to show that, if gamma entails A, and gamma prime is a superset of gamma, then gamma prime entails A, which is really just kind of trivial, right? I mean, you just kind of say it, but they struggle with it. It doesn't come naturally. You have to sort of get used to unpacking what this means is that for every truth assignment tau, if every formula in gamma satisfies tau, then so does A. And so to prove this, suppose this, then let tau be an arbitrary assignment, and it takes some getting used to, and so we push them to do it, and they do. Right. Or even similarly for first order logic, you have again the same fact about substitution that we just mentioned. We ask them to show that this is true in any model for all xa implies that A holds of any t. And again, it's just a couple of lines, but it's not easy for them. So we really push them to to work with semantics, work with the definitions. Okay. I mean, also, as I said, we show them DPLL, and we show them how you can extract a resolution refutation from a failed search. And there's kind of a technical claim that if you have a resolution refutation if you can refute a clause C under the assignment which sets P to true, and another clause D under the assignment which sets P to false, then putting them together, you can somehow find a clause E and a refutation of E under the assignment tau. And we give them all the pieces they need, but it's not a long proof, but you really have to understand what the terms mean and talk about substitution and so on. And so they learn how to do it. Okay, as far as implementation, I mean, we start by just having do little bits of code in a functional programming language. So we asked them to find all the perfect numbers less than 1,000, and you can do this with a functional programming language and the right primitives. You can just do this with a line of code, so it's not hard. But it's just just getting them to learn the language. We give them things with binary trees and computing binary coefficients and so on. But then when we get to logic, we make them, so we never need substitution for propositional formulas. So we don't do it in the textbook. So we make them implement substitution for propositional formulas. Or, we code up the evaluation of propositional formulas, but we also define conjunctive normal form formulas. So we make them just, code up the evaluation for CNF formulas. And then other things, just syntactic things. So when we do sat solving, we tell them what an autarky is. And I didn't know what an autarky was before this course, but Marine tells me. But roughly, it's if you have a CNF formula and a propositional assignment. Tau is an autarky if every clause that it touches comes out true, it satisfies. So every clause that is assigned to by one of the values in this partial assignment comes out true. And so, we make them write code that tests whether something is an autarky. Or, given a CNF formula, we make them find all the pure literals in the formula. Okay. Let's see. So, yeah. So, and was I going to do that now? Maybe I'll. Yeah. Okay. I say I'll show you. So I'll do that. So there's another thing we do is let me show you this. So there's a wonderful program that goes back to the 90s called Tarski's World, which I found to be great for teaching logic. You kind of create a blocks world and you put down blocks and you ask students to evaluate it. There we go. And so I found that it was actually very easy to implement in Lean. So let me show you our little implementation. So where was it? It would be implementing first order logic, Tarski's World. So given the semantic evaluation in a model I showed you, it's, you define, shape and an object as just, has a shape, size, and row and column. And so it's easy to code up, with what we have, you just code up Tarski's World. But the net effect is that what you can do is you can create a world. You can say this world has a medium-sized tetrahedron and 0, 2, and so on. And then when you evaluate it, you get the evaluation here. And Wojtek showed me that you can actually pin the window, and so that you can and then you can go down, and then you can just kind of evaluate the formulas in the world. So some of them come out true. This one comes out false, and you can kind of change the you can change the objects. Well, let me just change this. Let me change the dodecahedron to a cube. Right, and it changes there, and you can sort of add objects. Right, and so this means you can give students exercises. The examples, where are the exercises? Oh, whoa, that's the wrong file. Oops. Okay, sorry, that's a bug. I put the wrong. But anyhow, for homework assignments, you can basically give them puzzles where you give them constraints and then you require them to cook up worlds satisfying those puzzles. Okay. Oh yeah, and I said we also give students a partial implementation of Fourier-Motzkin and ask them to fill in the rest. So. Let's see. So where did I do that? So that would be under decision procedures, Fourier-Motzkin. And yeah, so it's a simple version of linear. Oh, let's see. How do I unpin? I don't know how to unpin things. Okay. It's a simple version of linear arithmetic. So you've got linear expressions like 3x plus 4y minus 4z, plus minus 2y. And there's less than and equal and comparisons. And we give them code to sort of eliminate equalities. But the two things that we leave out are where are the parts we leave out. We make them write a function for homework that basically given a list of linear expressions interpreted as the inequality, that expression greater than 0, divides it up into 3 bins. One where variable x doesn't occur at all, one where it occurs with a positive coefficient, one where it occurs with a negative coefficient. And then using that division just to eliminate the x from all the constraints. So you pivot on x and so on. And again, they can do that. And with the editor interface, they can write the code. And then you can always, in using Lean in the file, you can just kind of evaluate and just kind of test your code as you go. Right. So we asked them to do that. Okay. And finally, we show them. So that was the implementation. So the third part of the class is using them, just showing them to use external tools like SAT solvers, SMT solvers, and first order theorem provers. So we show students, for example, how to use SAT solvers to solve Sudoku puzzles. So I'll show you that in just a second. And then we'll look at a couple of the assignments that we asked them to do for homework. So let's see, let me bring Lean back. So this was the examples using SAT solvers, Sudoku. Okay. Yeah, so this is just code that, I mean, Wojtek wrote this code, very beautifully written, lean code that we take them through and we tell them what a Sudoku puzzle is and how to code up. But this basically has the effect of, so here's the encoding, that given a Sudoku puzzle, so here is now, you code it up, you give them a literal, you sort of put them, you say that, position 0, 1, you put the number 3, and 0, 3, you put the number 2. So it's kind of a little bit annoying. You have to give the, oh, you know what, sorry, let me actually show you this in the textbook so you can see the text that goes with it. So here's the textbook. So where is it using SMT solvers, using SAT solvers. Sorry, let me make this bigger. Hope you can see this okay, but yeah, so here we give them the text on let's see, CNF formulas, Sudoku puzzles, and so on. So we show them a picture of a Sudoku puzzle. We describe the encoding there, right? So we're really kind of then following up with that. But the nice thing is then you can just do the evaluation. So set the dimension, and you what do? You basically take the constraints plus all the unit constraints. These are the initial placements that they were given. And you show them that, just like that, you can get a solution to a Sudoku puzzle. So that, we do in class. And then for homework, let me see if I can show you this. Maybe I'll even show you this. Did I get rid of it? Let me find it on Marion's homepage, assignments. So I think it was assignment 6 was the, yeah, so, I mean, this is going to be too small for you to see. But on this assignment, so we talk about grid coloring. So the idea is you want to color rectangles with colors in such a way that there's no rectangle such that the 4 corners all have the same color. So you want to avoid monochromatic rectangles. So rectangles with, so again, you've got a grid, you've got an n by m grid, you've got k colors, and you want to color the grid with the colors in such a way that if you take any rectangle, the 4 corners are not all the same color. Right? So that's the puzzle. We tell students, code that up. And based on what they have with the Sudoku puzzle, we give it to them in parts. We say, code up this, code up that. But by cutting and pasting the Sudoku code, they can figure out how to write down the constraints for this. And then they, send it to a SAT solver and get an answer. I'm sorry, I'll just do the same thing. And so NumberMind is very similar. It's like Mastermind. The constraints are, you've got how does it work? So yeah, you've got a secret number that has digits. And then there are guesses, and then for each guess you're told how many correct guesses there are. And so from a list of number guesses of a secret sequence of digits and correctness, you've got to use a SAT solver to figure out what the number has to be. And again, it's very similar. They have to code up the constraints. Here they have to use at least and at most, right? Because the solution tells them that of your guesses, exactly 3 were correct. So they have to code up the formulas that express that. But they do it, and then they turn in the homework, and they've done that. Okay. Couple more examples. SMT solve. We show students how to use SMT solvers to solve magic squares. Again, let me just show you that because it's kind of fun. So here, using SAT solvers, using SMT solvers, magic squares. Put over here, close that, don't save, okay. So the same thing, magic square, we show them, give them code to do it. And here pretty much the interface, we show them how to do, we give them interface for writing S expressions in a convenient way. from within Lean and preparing, a list of S expressions and sending them out. And then really, the output as well. So if you look at what the code does, it shows here's the thing that you're sending to the SMT solver. And the SMT solver, here's the response. It gives, we use bit vectors. Turns out that they do better with that. But then we also give them code that reads back. Oh, we did this for the SAT solvers as well. That we gave them code that would kind of read back output from the SAT solver. And then you can reinterpret it. And there at the bottom, make it a little bit bigger, you can kind of see the resulting square. And the cool thing is, if you change it from 3 to, I don't know, to if you want a 6 by 6 square, you change the numbers to 6, and you let Lean run for a little while. And lo and behold, at the bottom, you have there's a 6 by 6 magic square. And I think it just takes a few more seconds. I think, I've done up to 10 without trouble. So we'll see if this comes back in a few seconds. But again, so we can show them how to solve magic squares and code it up and give them that example. Is it going to come back? Well, all right, we'll see if it comes back in a few seconds. I'll show you another example in a second. But for the homework, we have them packing almost rectangles into an almost rectangle. So let's see, where can I show you that? So almost rectangles. So I guess we're doing that. I guess this is the last assignment. So the idea is, so an almost square is a square for n is it's a rectangle of size n times n plus 1. So it's just one off. It's a rectangle where the width is one more than the height. And the game is you want to pack consecutive almost squares into an almost square. So for example, this is an almost square of order 4, so it's 4 by 5. And you can see it, you can tile it exactly with a 1 by 2, a 2 by 3, and a 3 by 4. And so that was the homework. The homework was just to do that for like an 8 by, so I guess it's, you can do, well, so you can do the almost squares of size 1 to 20 in an almost square of order 55. That really pushes the SMC solver to the limit. But in very little time, you can get an almost square of order 15 with the almost squares of order 1 to 8. And so, one part of the last homework assignment is to do that. We also show them in SMT solvers how to confirm the correctness of a procedure in Hacker's Delight. So there are a lot of these, these kind of clever hacking tricks to do things efficiently. So the one we show them is, Hacker's Delight, you can find an inscrutable bit of code that will count the number of bits that are set to true in a 32-bit vector. Right, and so we show that you can verify the correctness of that thing just by expressing the formula in an SMT solver, expressing a naive counting method, and then asking the SMT solver with bit blasting just to show that the two come out the same. And again, you show them in Lean. It's you just put it up on the screen and there it is. And you can show them that if you change any of the parameters, then the SMT solver tells you that it's not equivalent, that the code doesn't work, and it immediately gives you a counterexample, which is nice. Okay. And then the final thing, so there's just one last story I want to tell, is the last thing we get them to play with is vampire, so a first order theorem prover. So we give them the Aunt Agatha problem and a Smallian asylum problem. And again, where did my Lean go? Let's see, first order logic, where would it be? Using first order theorem provers. So here's, the Aunt Agatha. So I believe that, so this is commonly used in TP demos. So I think it's the example is it's in a talk by Peter Baumgartner. So I think he's to be credited with the example. But I'll show you that in the textbook in a second. It's basically a murder mystery and so on. You have to figure out who did it. And actually this, yeah. So you push vampire. So if you ask vampire if the butler did it, vampire comes back and says, no, I don't think the butler did it. What did it do? So refutation not found. Yeah. If you go to the end, if you ask vampire, it actually goes to saturation and actually decides that the butler, you can't determine that the butler did it. And in fact, if you negate this, then vampire comes back immediately and tells you that it can prove that the butler didn't do it. Yeah, it was suicide. Agatha, killed herself, and vampire will tell you that right away. So it's easy to code up first order problems and send it. So let me just make that just a few minutes left. Let me show you that. So so this is using first order theorem provers. And let me make it bigger. So the puzzle that was coded up is, someone who lives in Dreadberry Mansion kills Aunt Agatha. Agatha, the butler, and Charles live in the mansion. They're the only people there. A killer always hates his victim and is never richer than his victim. Charles hates no one that Aunt Agatha hates. Agatha hates everyone except the butler. The butler hates everyone not richer than Aunt Agatha. The butler hates everyone Aunt Agatha hates. No one hates everyone. Agatha's not the butler. And so, with our syntax, we can code that up as a list of formulas, and easily send that to vampire. So we also coded up in this example. Raymond Smullyan has lots and lots of wonderful logic puzzles that are easy to code up and use. So he's got one that he published in an article, one collection of puzzles that he published in the American Mathematical Monthly, called The Asylum of Dr. Tar and Dr. Feather. So these are insane asylums. Every inhabitant is either a doctor or a patient. Every inhabitant is either sane or insane. Everything that the sane inhabitant believes are true. Everything that an insane inhabitant believes is false. And then there are puzzles based on that. So, in one asylum, you have these constraints that, given any two inhabitants, A and B, either A trusts B or he doesn't. Some inhabitants are teachers of other inhabitants. Each inhabitant has at least one teacher. No inhabitant A is willing to be a teacher of inhabitant B unless A believes that B trusts himself, and so on and so forth. And it turns out from these constraints that you can derive that either one of the patients is sane or one of the doctors is insane. Again, easy to code up with a list of formulas, send it to vampire, and vampire verifies that fact. So we put this in the textbook. I'll be doing this in the lecture, next Tuesday's lecture. We'll be showing them this. And so for the homework, we gave them the last puzzle in the asylum. And it's a long story. The last asylum Craig visited, he found to be the most bizarre at all. The asylum was run by two doctors named Tar and Feather. The other doctors on the staff, an inhabitant was called Peculiar if he believed that he was a patient. An inhabitant was called Special if all patients believed he was peculiar, and no doctor believed he was peculiar, and so on. So he tells this kind of complicated story, and Dr. Tar and Feather make assertions. And so the puzzle is Smullyan asks you to show, well, he says, Craig realized the horror of the situation. What was it? The horror that he wanted you to realize that in this insane asylum, all the patients were sane and all the doctors were insane. Right? And so we made up a homework assignment and asked the student to show that conclusion follows. Right. So from the constraints, all the patients are sane and all the doctors are insane. But we did this actually before coding up the interface to vampire. We were a little bit risky. And the next day, Wojtek did the code that would do that. And then he typed in all the constraints and he said, well, there's got to be something wrong because the hypotheses are inconsistent. And he came back a few minutes later. He said, oh, wait, I corrected some typos. But wait, the hypotheses are still inconsistent. And I took a look at it and I couldn't find anything wrong with it. I stared at it for a long time. This was on Friday. I sent the puzzle to a couple of students of mine. Said, take a look. Do you see anything wrong with this? It turns out in this puzzle, so this puzzle it was published in the American Mathematical Monthly. It's in a puzzle book, The Lady and the Tiger. The hypotheses are inconsistent. There is no such asylum. So Vampire caught the inconsistency. And the next day, a couple of people I contacted, so Alex Bentkamp and Sol Bake, actually came up with pen and paper proofs that, in fact, there's a bug in the puzzle. The constraints are inconsistent. So we had to modify the homework assignment. Now we ask students to show that the hypotheses that Smolian made a mistake, that the hypotheses are inconsistent. But anyhow, so it's nice. It's a nice way to end the assignments for the class. Okay, so there we go. So that's pretty much it. So just to give you the conclusions. So I hope I've made the case that Lean is a great platform for teaching students about logic and its applications. It's nice as a functional programming language, but the imperative features are useful. The syntax was helpful for examples. Sorry, there's a typo there. But the interface, doing it in VS Code and having the continuous compilation was really useful. And the fact that we could use Lean as a theorem prover and do a little bit of theorem proving in Lean as well was kind of an added bonus. It didn't play a major role in the course, but we did, we did give it, but it did play some role in the class. And finally, let me just say that the class has been really enjoyable to teach. It's been really great. I mean, I think we've all enjoyed it. We enjoy teaching it. The students seem to enjoy taking it. I mean, the message is that, if you're going to teach students, I mean, so that it was important to me to teach the theory, right? To teach the mathematical theory of propositional first order logic. But the theory becomes a lot more meaningful when there's just kind of a smooth, direct transition to the applications, right? Because it becomes clear that the theory is needed for the implementations and the applications. I mean, you really need to understand what it means to be satisfiable and valid and in entailment and resolution proof and how it works if you're going to code it up and implement it and use it. And so, you have this kind of presentation where you're going from one to the other and seamlessly. I mean, it's, you tell them what a CNF formula is and how to put things in CNF, and then you code it up, and then you're using sat solvers and everything is CNF. So it's also very satisfying for students, even though all the programming examples we give them are small. It's very satisfying to just write little bits of code and just see the results right away. And things like Sudoku puzzles and almost squares and logic puzzles, even though they're toy examples, they're not just toy examples. I mean, students get the sense that, well, first of all, they're cool and they're a lot of fun, but they're general. I mean, you can code up anything, right? And so you've seen the small examples gives them a sense of the bigger examples, and so it's really a strong motivation for learning logic. So all the materials are publicly available. We'll keep working on them. So again, we just barely made it through the semester, but we seem to have survived, and feedback is welcome. So I'm sorry for going a couple of minutes over, but that's what I have to say. So thank you.
Thanks a lot, Jeremy, for the great keynote. Thanks a lot for accepting our invitation here. I think there is a lot to discuss, and the floor is open for questions. So I will start from the top left side of my screen. So let's start with Sebastian.
First of all, thanks for your talk. I'm not sure if I got it right. Do the students contribute to the textbook as well? For instance, by sending pull requests, or are they encouraged?
No.
They have to?
No, the textbook is we're just writing the textbook. So yeah.
Because apparently it wasn't the same GitHub repository. That's why I figured it might be possible to have students contribute. Maybe
no, the textbook is not in the same GitHub repository. Okay. Yeah.
Okay, so that's what I got wrong.
It was a part of the textbook. Yeah.
Thank you.
Yeah, it would be. I mean, so it would be nice to have a spin-off. I mean, there's so many logic puzzles you could code up. I'd love to have a repository. I'd love to have now a bigger collection of these. So I think it would be a nice idea to then have a companion repository set up where anybody can contribute more examples. Yeah.
Usually with student contributions to textbooks, the tricky part is quality assurance. That's why I was wondering what you do in that respect.
Yeah. So the textbook is all us. Yeah.
Thank you. We move to the second question, Tobias.
Hi, Jeremy.
Hey,
thank
Tobias.
you for this very nice overview of your course. As you said, you've used Lean 4 primarily for programming so far. How far do you want to push this in the direction of actually getting the students to do proofs? Because it'll require a deeper introduction into Lean, and therefore you can cover less material. So what is your expectation there?
Yeah, so what we've done in the class so far is there was sort of one lecture or so on using Lean as to do propositional logic. And then there was, it spread out across 2 homework assignments, but we had them do a lot of, propositional logic identities in Lean. And, they did that and they seemed to enjoy it. And in one of the remaining lectures, I'll try to do a little bit of first order logic. So show them equational reasoning and show them first order reasoning, maybe just to show them, how to do proof by induction on lists and so on. Yeah, the semester is just about over, so we don't have time to do that on a homework assignment. I guess in a future iteration, if we move things around, we might make space to have maybe one homework assignment with equational reasoning and quantifiers or something like that. In this class, I don't see it's really, this is an introduction to a lot of things. So it's really not, the focus really isn't on having it as a proof assistant. So really just to kind of show, just kind of give them a sense. But even so, once you show them that, then you can talk about the fact that, look, what's the advantage of having one system that's both a programming language and a proof language that, for you to express things. And you can talk about the fact that, well, now you can prove things about your programs. You can verify correctness. So in this course, it's really just to introduce them to the idea and get them familiar with the concept, and hopefully encourage them to take an interactive theorem proving class later on. But yeah, so otherwise it's a very kind of minimal glimpse at what you can do with a proofer.
Thank you.
We can move to the next question, Matthias.
So thanks for the talk. It was very interesting. I was really looking forward to hearing about Lean. I'm doing a course which is somehow related to some of the puzzles look similar for some of them, but I'm using Haskell. And I've always looked to Lean, in particular Lean 4, because Lean 3 is somehow, it's not obsolete, but it will not be developed any further. How stable do you think is Lean 4 now for using it?
So again, before we taught the course, we really agonized that it really is early. I think the biggest thing we worried about is the fact that there really is almost no doubt, very little documentation. So students, like if you teach a course on Haskell or Java, if students want to know how to do something, you go to Google and you find answers right away. So the software was, it was stable, not problematic. So the language is holding its own. It helps. Wojtek is involved with the Lean development team, and so we have an inside track. So it's still is early, but even at this stage, it was pretty stable. It held up just fine. I don't know, maybe, and it's getting better. I think 6 months from now, it'll be a lot more stable and so on. So it's still early. It's still pre-release. Documentation isn't there, but it worked well for us. I would recommend. Yeah, there are caveats. There's reason to have a little bit of concern, but like I said, it worked great for us, and so yeah, I would recommend giving it a try.
Okay, thanks.
Good. If there is no other question from the audience, I can ask one. We have seen during the workshop that there were different approaches for teaching, like some of the courses were more targeting the teaching from a theoretical perspective, some more from a practical perspective. You kind of reach a compromise between those, right? Is there anything you would like to change or something based? I know that probably you just joined the workshop due to the time zone,
yeah.
But would you can you comment on what you want to change in the future, if there is something you would like to improve with respect to how you merge all this theory, practice, and
Yeah, I am so happy with the way the course has turned out. I think it's, yeah, I mean, little things that we can tinker with and, fix typos and better explanations in the textbook and so on. But my favorite thing about the class was really this kind of the three strands and jumping back. And I mean, one advantage is, when students get bored with one thing, you switch to something else. So there really isn't any time to get bored with, if we spent all the time just coding up, Sudoku puzzles and so on, I think it would get boring. But, so the variation, I think, helps, keep up interest. But really just being able to go back and forth, again, to show the definition of a propositional formula, the mathematical definition, and then code it up and then use it. I found that very satisfying. So for me, I think that kind of that kind of interaction is really the most wonderful and interesting part of the course. So yeah, I do recommend trying to do something like that.
Joao?
Hi, thank you, Claudio. And thank you, Jeremy. Very nice talk. So I'd like to follow up on Tobias' question. So I know that the emphasis here is not really on using Lean to prove things, at least interactively. But I mean, do you have any experience teaching interactive proving using Lean? And does Lean 4 supports the structured proof format, or do students have to write proof scripts? I mean, do you have a recommended way on how to do it from your experience?
Yeah, so if you actually, at any point, if you send me email, I can give you more information. But the quick answer is I have taught courses. So one reason that we wanted this at the 200 level is, this is like a second year course that now students have room to go on to other things. They can take Marian's, SAT solving course. They can do bug catching, model checking, formal methods. I have taught interactive theorem proving classes based on Lean 3. Next semester, I'll probably be doing one, sorry, not next semester, in next fall, a year from now, I'll probably be doing one in the mathematics department at Carnegie Mellon, targeted to mathematicians. Yeah, I have used Lean 3, and I have a course I've taught a course called Interactive Theorem Proving, where I relied mostly on theorem proving in Lean and some other things. So I'd be glad to send you, more information. But yeah, you can. It makes for a great course. So I mean, a dedicated course on interactive theorem proving is definitely a good thing. And concretely, right now, the recommendation is if you want to do anything so Lean 3 has a substantial mathematical library, like 700,000 lines. Lean 4, the library will be ported, and yeah, Lean 4 that will have all the tactic proofs, structured proofs. So it's not backward compatible. The language is somewhat different, but I'll have, it'll be similar. But yeah, the advice is if you want to do a course on interactive theorem proving now, I would do it with Lean 3. But yeah, the port, it's within, we'll see, but within 6 months, we'll see, porting 600,000 lines in formal library. But it is critical path. A lot of people are working on it now. So when the port happens, go to Lean 4. Before that, use Lean 3.
Okay, thank you.
Good. Thank you again, Jeremy, for the great keynote.